Well, hi there. We have finally reached the end of lesson 5, and we're just going to finally get to the point where we can check endpoints of convergence intervals, because we have all the tests that we need to be able to do that, including conditional convergence, and just see what the implications of that are, including testing those endpoints. So just a quick review of the absolute convergence. So when we don't have a series where the terms are all positive, right? Then we are looking to check the absolute value of the limit. And so we say it converges absolutely if that absolute value of the limit is less than 1. And it will diverge if that absolute value of the limit is greater than 1. And if it's equal to 1 itself, absolutely, then we have an inconclusive test. So just reviewing the absolute convergence. And we had our theorem that said if you can show absolute convergence, then you have overall convergence at the same time. So it's always best to check absolute first, because if you can show absolute, then you have both of them. And if you can't show absolute, well, then you have to try showing regular. So absolute convergence means both this regular series and the series of the absolute terms will converge. If you have conditional convergence, only the original series will converge, but not the absolute. So we get to the alternating harmonic series that we've talked about before. Will that converge or will it diverge? So we've got to apply the alternating series test. Let's see if it checks all the check boxes for convergence. So the first check box is that it is alternating. And we have this term, so we recognize, yep, it's alternating. And the second check box is that it, other than the alternating part, all of the terms positive. So we look at this term, and that's for every n, it will generate a positive term. So yep, that's positive 2. Okay, and then are these terms decreasing? And yes, they are decreasing. And finally, not just decreasing, but are they approaching 0? And as the denominator grows infinitely large, then the value grows infinitely small. And so we know that the alternating harmonic series does converge. But what if we put the absolute values on it? Okay, well, now we got to check as going from n to infinity. Let's put the absolute values on this, which is effectively eliminates, and then another absolute value around 1 over n. So this whole term is going to be guaranteed to be positive. This term is already positive, so this would be equal to all right, and then we as the alternating part is gone, we're really just left with 1 over n, which is the harmonic series, and we know that that diverges. And so since we have only one kind of convergence, it's just one and not both, so let's look back. We call that, the conditional convergence. So we say it converges conditionally. Okay. Now, how do we check for these endpoints? The endpoints are going to come when we're looking for an interval of convergence. We always start with the ratio test. We find the values for which it will converge absolutely. So we're going to set up the absolute value of that limit to be less than 1. This will give us an open interval, right? So the inequalities are open here. In some instances, we will converge for all values of x. That would be when the radius was equal to infinity. And then sometimes the series will converge only at the single center value of a, and so that would be when your radius turned out to be 0. Okay, now if we come up with a finite interval, so we've got 2 endpoints on the interval, we want to test for convergence at each endpoint. Clearly the ratio test will already have failed us at those points, so we want to use the integral test, the alternating series test. We could use the limit comparison test. So some other comparison test other than the ratio test to see what the endpoints are going to do. So let's check that out. So we're going to find the ratio test first, the interval of the open interval, I should maybe specify. Okay, that is going to be an open interval of absolute convergence, and then we'll check the endpoints. All right, ratio test. Okay, we need to take -1, and we're going to add 1 to that, so that would be n plus 2. And then times x to the 2 quantity, n plus 1, over the term 2 times n plus 1. And then we're going to multiply that by the reciprocal, 2n, -1 to the n plus 1, and x to the 2n. So let's simplify all of these. Okay, when we look to reduce -1 to the n plus 1 and -1 to the n plus 2, that reduces to simply -1. When we reduce our x terms, that will leave me with x squared. And then we have the quantity 2n over the quantity 2n plus 2. As n approaches infinity, we can divide through by the highest power of n. So I'm going to have the limit of 2 divided by n, 2n over n. So if I divide, that's 2 over 2 plus 2 over n, and then I still have -x squared. So this limit here is going to be 1, and we have -x squared, but I want to check the absolute convergence on that. So the absolute value is x squared less than 1, so x is the open interval between 1 and 1. Okay, now we want to check our endpoints. So I'm going to slide over here and give myself some space. Let's check the endpoint, -1. So we're going to plug that back into our sigma, and we're actually physically going to put the x value as -1. So that would be -1 to the n plus 1 times -1 to the 2n, that's going in for x right there, over 2n. All right, what happens here? -1 to the 2n, no matter what n is, when you raise it -1 to the 2 times that, you're always going to have a positive number. And so that will always be +1. Let's see, we have -1 to the n plus 1 over 2n. I'm going to take this 2 and pull it outside of my series. So I'm going to have 1/2. And then maybe I'm going to write this as times 1 over n. So then I recognize this as being alternating, that's this part, and harmonic, that's this part. So I have an alternating harmonic series. And an alternating harmonic series does converge conditionally. So that endpoint will converge conditionally. Okay. Then my other endpoint was x equals positive 1. So let's check that one out. So negative 1 to the n plus 1 times positive 1 to the 2n over 2n. Well, positive 1 to the 2n is always going to be positive 1, so I really end up with the exact same thing. I end up with the alternating harmonic series, which also converges conditionally. So since both endpoints have conditional convergence, they can be included in our convergence interval. And so we summarize and we say our convergence interval is going to include negative 1 and it will include positive 1. So for x anywhere between negative 1 and 1, including negative 1 and 1, we're guaranteed to have convergence, at least conditionally, within that closed interval. All right, let's try another one. We're going to apply the ratio test. So we'll have x minus 3 to the n plus 1 over 2 quantity n plus 1 times the reciprocal of the other term. And after we reduce the terms, we'll have x minus 3 times 2n over 2n plus 2. And this portion here is going to have a limit value of 1, so we'll be left with x minus 3. So we want to have the absolute convergence be less than 1. Which means centered at 3 between 1 and negative 1. So x is bounded between 4 and 2. So our radius of convergence is 1. Our interval of absolute convergence is between 2 and 4. Okay, this is the interval of absolute convergence. Now we want to find out if we can extend this interval to include the endpoints or not, and possibly to have conditional convergence at the endpoints. Okay, so I'm going to use my scratch or my extra paper over here, extra space, and we're going to check 2 and we're going to check 4 and see what happens. All right, checking 2. So when I substitute 2 in for x, I'll get 2 minus 3 to the n over 2n, which will give me negative 1 to the n over 2n. And by the same reasoning that we had before, we have an alternating harmonic series, and so this will be conditionally convergent as we recognize the alternating harmonic conditionally convergent. So far we'll be able to extend our interval to include the endpoint of 2. All right, now let's check the endpoint of 4. So that will be 4 minus 3 to the n over 2n, which gives me 1 to the n over 2n, which is a positive number. So I'll have 1 over n. This is straight out harmonic. And this is going to diverge. So the endpoint of 4 would produce a divergent series, whereas the endpoint of 2 would produce a conditionally convergent series. So my overall interval of convergence can be expanded to include 2 as conditionally convergent, but I'm still not going to include 4 because it diverges at 4. All right, let's give this one a try. We're going to once again apply the ratio test here. All right, so we've got 10x to the n plus 1 over the factorial n plus 1 times n factorial over 10x to the n. And reducing, that leaves me with the single quantity 10x over n plus 1. And when we put in infinity plus 1 over, it really is irrelevant what the numerator is, because the denominator is going to become so large that we're going to be approaching a limit value of 0. So if we approach a limit value of 0, then we know that this is has an infinitely large radius of convergence. And so this thing is absolutely convergent for all real numbers. It has an infinite radius of convergence. That means no matter what x value you could think of to put into this series, it will produce an absolutely convergent, and if you're absolutely convergent, then you're fully convergent series. So there's nothing you could come up with that would make this series diverge. It will always be an absolutely convergent series. All right, so I'd like you to maybe try on your own a couple of these summary questions that kind of look back over the last few weeks and what we've done. I've picked out, I didn't pick all of them, but I picked a few of them, so 5 of these summaries. And then I did also include the answers if you want to check yourself, just to kind of give a pulse of where you're at so you have an idea of what you really fully understand and what you maybe need to go back over. Okay, and then we'll come back together on Friday, tie a nice little bow on this 9-5, this 9-4 and 5, I think, things on all the different convergence tests that we have. And then we are really in the home stretch, because all we got to do is go back and look at 9-2 and 9-3, and we're done. So hope you have a good rest of your Thursday, and I will see you on Friday.